This video shows you how to set up a problem simulating a draining tank using moving mesh in Comsol. Start by adding a component. This will be a 2D problem, so put in a 2D component, and then we'll need to add some physics. So we'll go to fluid flow, multi-phase flow, two-phase flow, moving mesh, and the laminar version of that. Select that. Now we'll include a time-dependent study. The geometry will be a rectangle that's 1 meter by 1 meter. And we'll need to add a point so that we can have a small place down in the lower right hand corner that is where the fluid will drain from. So we'll put a point in the geometry, and the point has locations shown there. It's only 2 millimeters above the upper corner. So it's down in the, or 2 meters above the lower right corner. So we can see this point down in the lower right corner if we zoom in a little bit. So we magnify the corner and you can see that point there. We'll go and we'll build the rectangle alone, and then we'll build it with the point. You can see that point there. So we've added a moving mesh. The entire region will be the deforming domain, and we've added some mesh slip boundaries. The two sides will be mesh slip boundaries. So you can see the two sides there, and we have to go in, zoom in, and get that little piece down there where the drain is. That'll be part of the mesh slip boundaries. The laminar flow physics we set up using similar approach. We have to define the fluid properties. So we'll go up to materials, and this is a gasoline tank that's leaking. So we want to see if we can find the properties for gasoline. If we go to liquids and gases, we'll find it under liquids, and if we scroll down, there's the properties of gasoline, and we can select that, and that'll give us the properties that we need for this particular problem here. So we put in gasoline, and then when we set up the fluid properties, we can use the density and viscosity from material. That'll draw on the gasoline. We need to make sure that the gasoline under materials is that we select the rectangular domain. Now we need to make sure also that we include gravity under the physics node. That'll produce a page that looks like that, with the G underscore constant as the gravitational constant. We'll have slip boundaries on the walls, and the outlet is going to be specified as 0 pressure, and we highlight the edge down there in the lower right hand corner. It's edge 4 in this simulation. We also need to select the free surface boundary condition. This ensures that the mesh is going to move with the fluid. And then we're just going to use a physics controlled mesh for this problem with a normal size. It's a time dependent problem, and we'll run it out for 200 seconds. The solution I have set up here with some streamlines, and the pressure distribution is shown there. And we'll see it start to kick in here where the tank starts to drain. There we go. That's what the fluid looks like as the tank drains. So when we plotted this, I plotted the velocity as log 10 of the velocity. That's because if you plot the velocity just with the normal scale, it looks like this. And that's because the velocity is fast right around the leak, but it's pretty slow everywhere else. So that's why I used log 10. I also include streamlines that show the path of the fluid, and I have the streamlines originating on the boundary, and I use the top surface boundary, which is boundary 3. Okay, let me show you how to visualize the mesh. This solution works by deforming the mesh, and we can see the mesh if we click wireframe on the surface plot. And there's what it looks like. It's the same color as the color flood, but that makes it kind of hard to see. So I'm going to take the log 10 off so it's dark blue, and then I'm going to take the streamlines off, and now you can see the mesh a little bit better. So I'm going to run it back to 0 time. That's the original mesh. And now if we step forward in time, let's get it so we can see it a little bit better. We step forward in time and we can see how the mesh is deforming to track the fluid boundary. The mesh gets really pretty deformed by the end of the simulation. We also want to determine the volume or the surface area of the region with time. So we select it, we're going to do a surface integration, and if we just use 1 as the integrand, this will give us the area, and we integrate that with time, and there's the surface area. If we plot that, there's the surface area as a function of time as this tank drains. So if it was 1 meter wide, then this would be, this is in units of square meters, but if the tank was 1 meter wide, then it would be cubic meters.